All right, let's go ahead and get started. I do want to welcome to this worksheet. This one is simply called pH. We won't need a calculator or even a periodic table for this one, so let's go ahead and get started. Well, what do we mean by pH? The concentration of hydrogen ions in an aqueous solution can be measured on the pH scale. So the pH scale we can think of as going from a low of 1 to a high of 14, with 7 being the neutral pH, right? Now, there are such things as pH is lower than 1 and certainly higher than 14, but we're going to focus on that scale right there. So from 1 to 14, we call acids, and from 7 to 14, we call bases, with neutrality occurring right in the middle. All right. So the higher we go on the pH scale, the more basic. So something that has a pH, say for example, of 13 is more basic than something that has a pH of 8. Something that has a pH of 2 more acidic than something that has a pH of 6. Neutral, having the same concentration of hydrogen ions as hydroxide ions, is 7. So when we measure pH, what we're really measuring is hydrogen ions and hydroxide ions. So on the left-hand side of the scale, we're going to have a high number of hydrogen ions. So we have a high concentration of H+, and on the right-hand side, we have a low concentration of H+, but a high concentration of OH-, just like that. Values greater than 7 have excess hydroxide ions and are considered basic. Values less than 7 have an excess of hydrogen ions, are considered acid. Label each of the following items as A if it's acidic, B if it is basic, or N if it's neutral. Seawater. Seawater has a pH of about 7.14. It's a little bit basic, not very basic, but it's a little bit basic. So we would call that basic. Lemon juice, acidic. All citruses are acidic. So we're going to call that one an acid. We'll label that with an A. Blood, also basic. Also basic. Slightly basic, a pH of about 7.4. And pure water, absolutely neutral. This is the one that has the pH of 7. Now, bear in mind, when we say pure water, we mean distilled deionized water, not the type of water that you get out of a tap. All right, so we're going to talk a little bit about finding pH now. What do we mean by that? Well, a simple way to find pH is to show the concentration in the molarity of the hydrogen ions in the solution in scientific notation. The opposite, change the sign of the exponent on 10 is the pH of the solution. So if we have a hydrogen ion concentration of 1 times 10 to the minus 4, the pH would be, well, we'll change the sign of the 4, so that's negative 4 becomes positive 4, so the pH is 4. Remember that everything below 7 is going to be an acidic pH, so we're going to call this one an acid, and we're done with the first one. The next one is, we'll go down from there, is 1 times 10 to the minus 10, or 10 to the minus 10, is going to have a pH of 10, right? So we're going to look to the exponent, and if the exponent is negative 10, it becomes positive 10. So 10 is the pH, and remember, everything above 7 is going to be positive, or basic rather. So that one is a basic pH. 1 times 10 to the minus 10 has a pH of 10, and if the pH is 10, then we have a basic situation. All right, the next one is 1 times 10 to the minus 7, right? So we'll look to the exponent. The exponent is negative 7. That means the pH is going to be the opposite in sign, same magnitude as that. So the pH would be 7, and that, of course, is neutral, so we'll label that as neutral. And finally, 1 times 10 to the first, or 10 to the first, is going to be 1, or it's going to be negative 1. So the pH is negative 1. So bear in mind, it is possible for the pH to be negative 1. We won't concentrate too much on negative pHs, but it is possible for it to happen. Just wanted you to be aware of that. That, of course, is acidic, right? So we're going to label that as an acid, and we're done with number 5. Let's look at number 6. Number 6 says, use the pH to find the hydrogen ion concentration for the solutions below. So we're going to go the opposite way this time. So if they give us the pH, for example, in A, they give us the pH of stomach acid as 1, then the hydrogen ion concentration is going to be 1 times 10 to the negative 1, or 0.1. So we're going to take the negative log, right? The negative log of that. So if the pH is 1, we're going to write the hydrogen ion concentration of 1 times 10 to the minus 1. I want to note that pH is equal to minus, and I've made this statement just a moment ago, is equal to the negative log of the hydrogen ion concentration, right? So if you know one, you know the other. Let's take a look at B. We have rainwater with a pH of 6. Now, what we're going to do is, if the pH is 6, we're going to determine the hydrogen ion concentration from this formula. So it becomes 1 times 10 to the minus 6. So if we have 6 for the pH, we're going to have a logarithm, or power, I should say, to the same thing, of 1 times 10 to the minus 6, and that'll do it for B. Let's look at C. Oven cleaner has a pH of 14. So the hydrogen ion concentration in oven cleaner is going to be 1 times 10 to the negative 14. So we simply take the pH and we raise it up as a power and change the sign. So it's 1 times 10 to the minus 14. And finally, for a banana, it has a pH of 5. So that would be a hydrogen ion concentration of 1 times 10 to the negative 5. And that'll do it for B. All right, let's take a look at number 7. Number 7 says, we will assume that the solute in each of the following solutions dissociates completely. Convert the concentration of hydrogen ions to scientific notation and determine the pH. So here we go. So they're telling me that the concentration of the solution is 0.001 molar hydrochloric acid. So they want to know what is the hydrogen ion concentration. And so I'm simply going to say, well, if this is a strong acid, and it is, then the hydrogen ion concentration is going to be the same as the H plus, or the molarity of the hydrochloric acid. So if the molarity of the hydrochloric acid is 0.001, I have a hydrogen ion concentration of 0.001. If I change that to scientific notation, that's 1 times 10 to the minus 3. I just moved it over 1, 2, 3 places to the right. So that would be 1 times 10 to the minus 3. And of course, the pH is going to be 3 for that one because I'm looking at the exponent. So the pH would be 3 for 0.001 molar hydrochloric acid. If we have 1 molar HNO3, that's nitric acid, we're going to have a 1 molar hydrogen ion concentration. Since nitric acid is also a strong acid, right? Like hydrochloric acid is a strong acid. So the molarity of the nitric acid is going to be the same as the concentration or the molarity of the hydrogen ions in that solution. So we have 1 molar. Anything to the power 0 is 1, so that would be 1 times 10 to the minus, or 1 times 10 to the 0 molar. So the pH is going to be 0, just like that. And finally, we have 0.05 molar sulfuric acid, 0.05 sulfuric acid. Now, I want to talk just briefly about why the hydrogen ion concentration is a little bit different than it was in the previous two. If, for example, I have hydrochloric acid, so we'll take that example. So hydrochloric acid is a strong acid, and it's going to dissociate completely into hydrogen ions, and I'm going to draw it like this, plus Cl minus. So the concentration of the hydrochloric acid and the concentration of the H plus is the same. But let's take a look at the H2SO4. The H2SO4 has 2 acidic hydrogens. It's H2SO4. So if I take a 0.5 molar sulfuric acid solution, what's going to happen is that the H2SO4 is going to dissociate into 2 units or concentrations of H plus, because of that 2, plus the SO4, of course, which I really don't care about. It's a spectator ion in this case. But the point is, I'm getting 2 hydrogen ions for every 1 H2SO4 molecule. And therefore, I'm going to double the concentration of the H plus from what the concentration of the H2SO4 was, so I get 0.1. In scientific notation, that is going to be 1 times 10 to the minus 1, and so the pH is going to be 1 for that. Okay, very good. Let's go to number 8. Number 8, it says a pH or acid-base indicator is a compound whose color changes with the pH. State this color of the named indicator at the stated pH. All right, so here's what I want you to know. I want you to know that if you have a pH that is acidic, as is the case with a pH of 4, right? If you have a pH of 4, blue litmus paper will turn red. Blue litmus paper will turn red under acidic conditions. Likewise, we're looking at B now. If you have litmus paper at pH 13, red litmus paper will turn blue. Red litmus paper will turn blue. So litmus paper is one indicator, but so is phenolphthalein, another. So let's take a look at C, phenolphthalein at pH 5. I want you to know that phenolphthalein, when it's under acidic conditions, is colorless. So at pH 5, it's going to be colorless. And finally, phenolphthalein at pH 11, when it's basic, it will be pink, right? As you go higher and higher and higher, it'll turn from pinkish to almost red. But certainly at pH 11, we're above 7, so it's going to be pink. That'll do it for number 8, and that'll do it for this worksheet. I'll see you in the next one. Thanks. Bye-bye.